Have you ever ripped open a fresh bag of mixed candies, hoping for a handful of your favorite color, only to find just one or two hiding at the bottom? It feels like bad luck, but candy factories actually follow a strict recipe. They set a specific mathematical rule that dictates the exact percentage of each color that should go into every bag. This chart shows the manufacturer's official published breakdown. For this specific brand, they claim every batch is 24% blue, 13% brown, and 16% green. In statistics, we call this published factory rule our expectation. It is the mathematical standard that tells us what a perfectly balanced world should look like. But let's look at the candies we just spilled onto the table and sort them into distinct color piles to see what we actually got. Looking at our piles, something looks wrong. The brown pile is massive, taking up almost half the space, and we only have a tiny handful of blue candies. This leaves us with a choice. We have to decide if the factory changed their recipe or if we just happened to buy one weird, randomly unlucky bag. We call these messy, hand-counted piles our observed data. Now we have a clear conflict between the perfect ratios we were promised and the uneven bag we observed in real life. Let's put our factory expectation on the left and our observed reality on the right. A bag this size should have 52 blue and 28 brown candies, but our real bag gave us only 31 blue and a massive 63 brown. Statisticians use a specific mathematical tool called the chi-square goodness of fit test to look at these types of differences. It has one single job. It measures the size of the gap between the perfect expectation and the messy reality, checking to see exactly how good our data fits the rule. If we are missing just 2 blue candies, the test counts that tiny gap as normal variation. But with an extra 35 brown candies, the test flags the gap, recognizing a difference that massive is unlikely to be an accident. The test accounts for every color in the bag simultaneously, calculating and adding up the differences across all groups into one final score. This makes the test an objective judge. It removes our human tendency to guess, drawing a clear mathematical line between what is just random chance and what is clearly a broken rule. Let's run our actual candy counts through the software to get an official answer. This table shows the final output from the test. You can see the software lines up our exact observed candy piles directly next to the factory's expected numbers, column by column. Up at the top, the final score tells us the probability that this giant gap was a random accident. The result is 0.001. This number represents the chance of getting a bag like this if the factory was actually following its own rules. Since that chance is less than 1 in 1,000, we know the difference is far too large to be an accident. We have our verdict. The evidence proves that our real bag does not match the manufacturer's official proportions, so we can no longer accept their rule as the truth. While we used candy to see how the math works, data analysts rely on this exact logic in the real world. They use it to verify corporate claims, ensure fairness in hiring pools, and audit marketing data to see if reality matches the brochure. To run it, you always need 2 things: an expected baseline rule and real-world observed categories to hold up against it. The chi-square goodness of fit test gives us the power to mathematically prove when the real world stops following the rules we expect it to.